Greetings to all of you. This is Sarwar Hussain Nehru, and I'm going to throw light on the topic smart metering system capable of anomaly detection by bidirectional LSTM autoencoder. Before we move towards our presentation, let's have a look at the table of contents. First of all, I will go through the problem statement. Then I will tell you the aim of our study, followed by the modeling of our system, simulation results, and I will wrap up with the conclusion. Before we proceed, let me define the term what is a smart meter. A smart meter is a metering device that can measure and transmit real-time energy consumption information to utility providers, facilitating monitoring and control of power system. And let me tell you what is anomaly. Anomaly, also called as outlier, represents a data point which is considerably different from the other data. As you know, electric power consumption is increasing rapidly in urban areas due to the change of industry paradigm due to fourth industrial revolution, which requires increased power consumption. Therefore, more power facilities are newly established and the capacities of existing power facilities are being expanded. As modern society relies heavily on the utilization of electricity, power outages have had great impact on our lives. It is essential to manage the power system efficiently to provide reliable service to the customers. To solve this problem, smart meters are utilized to provide the users with power usage pattern, high frequency of power user information, and bidirectional communication between smart meters and meter data management system, and establishing a more trustworthy power system. Energy consumption of buildings often exceeds the specific value, representing energy savings due to anomaly. Even though the energy model of building is designed as a low energy model, to figure out these circumstances, anomaly detection is a helpful method to identify anomalous events. Let us have a look what is the aim of our study. This paper presents an anomaly detection process to find out outliers observed in the smart metering system. A bidirectional, long short-term, memory-based autoencoder is used and finds the anomalous data point. It calculates the reconstruction error through autoencoder with the anomalous data, and the outliers to be classified as anomalies are separated from the non-anomalous data by predefined threshold. In the third chapter, we are going to explain the modeling of our system. A smart meter, as I told you, is a metering device that can measure and transmit real-time energy consumption information to the utility providers, facilitating monitoring and control of power system. It is different from the traditional meter in that it can provide a wide range of advanced services such as remote connection activation, deactivation, and bidirectional communication between smart meters and utility providers. Data concentrator is a tool that is commonly found in substations and is used to manage the data collected from various smart meters in distant houses. The data concentrator primarily serves as store and forward link between the smart meter and the rest of the system, collecting data on energy expenditure at remote residences, transmitting the data to control centers, and providing the data to the billing systems. Now we move on to what is a central SS server. A central SS server is described as the central application which manages the information, assortment, control, and parameterization. The smart metering system features numerous ports through which information can pass to facilitate communication between system components and market parties. There are different ports. You can see port P1, port P2, port P3, and port P4. Port P1 is the read-only port to connect the metering installation with external devices. Port P2 is linked to other local metering apparatus. It can be used for wired or wireless communication with electricity, water, heating, hot water meters. Port P3 is used for two-way communication with distribution system operator, that's called DSO, to send information such as metering values, status, power quality, and outage measurements. Port P4 is a gateway for ISPs, energy suppliers, and grid operators to acquire measurements from port P3. In this slide, as I told you in the beginning, what is anomaly? As I told you, it represents data point which is considerably different from other data. An outlier is an observation that significantly differs from the others, raising concerns about whether it was produced by a distinct cause. As you can see in the figure, anomalies in the dataset of electricity, water, heating, hot water are presented. The anomalies can be observed as the deviation of the abnormal data from the normal ones. Here we can see the peaks in four types of datasets. In case of sample data, including outliers, there exist several characteristics such as large gaps between inlying and outlying observation data, and the deviation between the outliers and the inlier group measured on the standardized scale. The figure shows the structure of Bi-LSTM autoencoder. Power systems are being confronted with enormous information issues, and to deal with this huge volume of information, deep learning algorithms are the best arrangements. The unidirectional LSTM approach produces certain errors in the results as they utilize one-way memory. The Bi-LSTM approach is an extension of the traditional LSTM approach, which can improve the performance in the aspect of sequence classification by using the sequence information in both directions, that is, forward and backward directions. As shown in the figure, an LSTM cell has forget, input, and output gates for effective short and long-term cell memory. In particular, the training of LSTM memory block has two ways: one LSTM from past to future and the other one from future to past, possessing data from both the past and future at each time. In this chapter, I will explain the simulation results. In the smart metering system, data of electricity, water, heating, hot water are collected from 985 households. The training progress of the Bi-LSTM network is shown in the figure. The model is trained for 200 epochs with the specific byte size. Here we can observe that both the training loss and the validation loss decrease. The training loss is calculated by applying a mean squared error as a loss function to prevent inadequate learning such as local minimum and overfitting, dropout, and gradients are applied. Depending on the number of epochs, the decrease in both training loss and the validation loss describe that Bi-LSTM autoencoder is well trained. For training the Bi-LSTM autoencoder, 80% of the data samples are used for training and the remaining 20% of data samples are used for validation. The receiver operating characteristics, that is ROC curve, is able to provide information on the overall performance of the classifier. As you can see in the figure, the Bi-LSTM autoencoder has larger area under curve than unidirectional LSTM autoencoder with four types of energy sources, that is electricity, water, heating, hot water. This demonstrates that the Bi-LSTM autoencoder achieves better performance in anomaly detection than the unidirectional LSTM autoencoder. Anomalies are detected in four types of energy sources, as I told you, with the Bi-LSTM autoencoder by calculating the reconstruction error between input and reconstructed input. You can see in the figure dark blue dot, orange dot, and the thin red line is represent normal data, outliers, and threshold. When data points have higher reconstruction error than the threshold, they are classified as outliers. On the contrary, when the data points have less reconstruction error than the threshold, they are classified as normal data. There exist other outliers which are classified as normal data because of small reconstruction error, similarly observed with the normal data, and some normal data classified as outliers due to the reconstruction error above the threshold. Finally, we can see in the table that is the performance evaluation of unidirectional LSTM autoencoder and bi-LSTM autoencoder. Table shows the accuracy, precision, recall, F1, and MSC defining the confusion matrix. The accuracy, precision, recall of the bi-LSTM autoencoder is higher than the unidirectional LSTM autoencoder, and the mean square error of bi-LSTM autoencoder is lower than the unidirectional LSTM autoencoder. Finally, we wrap up the summary with the conclusion that in this study, a novel method of anomaly detection for smart metering system is proposed. To find anomalies among data sets measured by smart metering system, the bi-LSTM autoencoder is utilized. To provide the comparative performance of the bi-LSTM autoencoder in anomaly detection, ROC curve and area under curve are calculated. Thanks for listening our presentation. Have a nice day.